taking a look at question 4 from the course Harmony and Partial Differential Equations. So this question is worth 50 marks. And yeah, let's just get straight into it. So the function u depends on two independent variables where u is a function of x and y. Find the general solution of the partial differential equation. Alright, so when we're dealing with the partial differential equation, the first thing to do is assume that u is the product of both a function of x and a function of y. So usually you do this. Now, in this situation here, this actually won't do too much because there's actually going to be no way we can get a function of x and a function of y all by itself. So the reason why we do this when we're solving a PDE, partial differential equation, is because we can usually separate one side of the equation to be completely x and one side to be completely y. Now, this is what I try to do on this equation, and we pretty much get a pretty similar thing like this, okay? But it's important to understand like why we still do this anyway. So here, that's all we're going to do is just find what these guys are. So we already know what u is, so we're saying u is this here. So now let's find these guys here. So the derivative with respect to x, the partial derivative, you just differentiate this with respect to x, which means the function of y is treated as a constant. So here, the f of x just turns into f dash of x. Okay. Likewise, if we want the second derivative, we do the exact same operation. Again, the function of y is treated as a constant. So here you just get f double dash of x. Okay. Now, when you substitute all this stuff in, not much in terms of the structure is actually going to change. And I'll show you why in a second. So if I shove this all in, so we'll have f double dash of x, g of y, plus 3 f dash of x, g of y, minus 4 f of x, g of y, and I'll just make this a bit smaller. Equals 2x plus 3y plus 1. Okay, so here, what we can do here that's quite obvious is that all of them contain g of y on the left hand side. So if we want to, we could factorize that out and divide both sides by it. So here what we're left with is f double dash of x plus 3 f dash of x minus 4 f of x equals 2x plus 3y plus 1 all over g of y. Okay. Now here we have the exact same structure here that we do here. The only thing that's different is instead of partial derivative with respect to u and x, it's just a normal derivative with respect to x. Okay. So basically here what we have to do is we have to look for the homogeneous solution and we have to look for a particular solution. Okay. Now, it's good we have it like this, so we can find the homogeneous solution by pretty much saying, alright, this whole thing is equal to 0, and then using a characteristic equation, okay? So the homogeneous solution is basically saying, alright, this entire side here was just equal to 0, okay? So here, all we're left with is pretty much, alright, so we can make a characteristic equation out of this guy here. So the second derivative can be treated as, like I say, m squared. The first derivative can be treated as m, so we have plus 3m. And then the minus 4 f of x can just be treated as minus 4, okay? Now, the solutions to this characteristic equation usually go into a structure like this. So if we have y as a function of x, whatever the answers are to these guys here will pretty much be the powers of this exponential up here, okay? Now, the coefficients in front of these exponential terms, because this is just a function of x, however, we are dealing initially with a partial derivative. So basically we have a function of y here. But these coefficients aren't just going to be just normal coefficients, they are going to be functions of y. Okay, so this will be c1, but instead of just it being a constant, it is a function of y that we have no idea that could be there. Okay, same here. This could also be a function of y, so c2y. That's our general structure when we solve this characteristic equation for the homogeneous solution. Okay, so here, this is actually quite easy to solve. So here, if we just factorize this guy here, this can get factored into, alright, what two numbers multiply to give -4 but add to give +3? Well, +4 and -1. So here our m's would be 1 and -4. So these are the values that go in these powers here. So the solution that we have now, when we actually write our solution, we have to say, alright, because we're talking about a function of y and a function of x, this isn't going to be u of x. This isn't going to be y of x anymore. This is going to be u of x and y, because it's a function that depends on both of them. So our homogeneous solution is going to be a constant function of y, e to the power of negative 4x, plus a constant function of y, e to the power of 1x. Okay, and that's that first bit. That's a homogeneous solution. Now the particular solution is taking into account this stuff over here. So here we're going to assume, based on this guy's structure, we're going to assume another function u of x and y looks like this: ax plus let's go b, another wrote 3 there, by plus c. Okay, where these are constants. So what we're going to do is we're going to assume a solution takes on this form here, and we're going to shove it into our PDE. So if we just rewrite our PDE, so our partial differential equation, so it's I'll just write down here. So second derivative with respect to x, what was the next bit? Plus 3, this one here, minus 4u equals 2x plus 3y plus 1. So pretty much when we substitute this into the PDE, we're going to work out whatever these coefficients are going to be that satisfy it. Okay, then we'll have the homogeneous solution and a particular solution. So this is the particular solution, and this one up here is the I'm gonna spell that genius, I don't know how to spell it, homogeneous solution. We'll just leave it like that. Okay, so here let's find these derivatives. So here, if I were to condense this a little bit, the PDE, I were to say copy this guy here, plus c. So the first derivative, so this one here, differentiate with respect to x. So here, this whole term turns to 0, so all we're left with is just a really. And then the second derivative with respect to x will just be 0. Okay, so subbing this in is going to be quite nice. So that goes in there, this goes in there, and what other color haven't we used? This goes in there. So what we're left with is 0 plus 3a minus 4 times by ax plus by plus c, and this is equal to that right hand side. So it's equal to 2x plus 3y plus 1. Now we can equate the coefficients. So here, if we multiply this stuff out, we're going to get given, so 3a minus 4ax minus 4by minus 4c equals 2x plus 3y plus 1. So because we're equating coefficients, so I will move some stuff around so we can see it a bit better. So this, move it like this. So this here, so if I underline this, this coefficient is the only thing with x, must be equal to 2. This coefficient is the only thing with y, so that must be equal to 3. And this entire thing here is a constant, must be equal to 1. So from this we get negative 4a is equal to 2. We get negative 4b is equal to 3. And then we get 3a minus 4c is equal to 1. So from the first two equations we get a is equal to negative 1/2. This one here we get b is equal to negative 3 on 4. We can substitute this into here to solve that. So negative 3 on 2 minus 4c is equal to 1. So here we'll have negative 4c equals 1 plus 3 on 2. So here, if we were to add those guys together, you'll get negative 4c equals, what's that, 5 over 2. Divide both sides by negative 4. So you're going to have c equals negative 5 over 8. Okay. So our particular solution to this guy here will be taking on a structure like this. Oh, let me just go here. Let's get that. Plus c. So in this case here, we have, so a is negative a half, so let's just say this is another function. A is negative a half, and then b is negative 3 on 4, and then c we said was negative 5 on 8. Okay, and then that should pretty much be done. If you have any questions about what we've done here, we're not finished. We've got to combine it for a single answer. So if you want the general solution to the PDE, you need the sum of the homogeneous solution plus the particular solution. So here, the solution to the PDE would be these guys added together. Okay, so this, if I zoom out, is your overall solution to the PDE in question 4. Okay, alright. Yeah, if you have any questions about this one here, leave something in the comments and I'll try my best to answer it. But overall, treat it like any normal PDE, so assume it's a product of both. You'll still be met with this guy here because it's got that second derivative there, but it's more important to understand like why we go to the characteristic equation here, but more importantly, why we have the coefficients as a function of y and not just a constant, because it's a partial derivative. Even though this one here was regular derivatives, we got rid of that function of y by moving it across. Okay, alright, but I will see you in the next video. Okay.